Alright guys, hopefully third time's a charm. I lost the first attempt at recording this. The second one got interrupted by a very long conversation and I thought I paused it, and so anyways, didn't work out either. We're moving to chapter 12. Now chapter 12 seems like it's got a lot of rehash in it of chapters from the very beginning of the class. And what I mean by the very beginning of class, stuff that you hopefully learned in a prior semester, like what a double was versus a float, what an integer was versus a long, and why you might want to use a double. Why you absolutely do want to use a double is to avoid floating point rounding errors, or to minimize them, because a double contains more precise values. Why does it contain more precise values? Because it has more bytes dedicated to it. Just like if you had the value in base 10 and you only had 4 digits, right? Say you had 1 divided by 3. We know that that's 0.333 repeating endlessly. And say you had some base 10 data type that could have only 4 digits, right? So that's what that would equal. No, it doesn't. That doesn't equal it. And then you had another base 10 data type with twice as many digits. Something like that, right? I don't know if I got 8 or 9 there, whatever. It's closer, right? It's more precise. Still not the same, right? So the more memory that you can dedicate to a specific value, the more precise it can be. Now a double can hold up to about 15 or 16 places of accuracy, plus an exponent, because it is a 4-byte data type. Excuse me, an 8-byte data type, right? Double is 8 bytes, whereas a mere float is a 4-byte data type. So, and a long is got 8 bytes. Can I type? Long is 8 bytes. And an int is 4 bytes. Right. Now that doesn't mean that an integer can only hold 4 digits, right? In actuality, it can hold up to about 10 digits. 10 digits being up to about 2 billion. So an int is good for values of up to about 2 billion. If you need more data, you're going to use a long. Similarly, a float is accurate to about 8 digits of accuracy. Point followed by 8 decimal places. Whereas a double, since it has twice as much memory allocated to it, can hold up to about 15 digits of precision, plus the exponent. So the slides start off showing something like that, right? An integer, has got an int has got 4 bytes, 32 bits, so it can go from about -2 billion to +2 billion, right? 9 decimal places. A long can hold many more digits, right? Now the cool thing about ints and longs is that they are pretty much precise, right? If you have 2, then you have exactly 2 of something, because they're whole numbers, right? And so doing math with ints and longs should be precise, right? There should be no rounding errors. Floats do give you rounding errors. So a 32-bit type, which is 4 bytes, is a float. It can hold, like, the maximum value is 3.4 to 10 to the 38. This is the thing to remember, that 38. Exponent 38 is a float. And it can hold, like I said, about 8 digits of precision. So, 8 digits there, 3.444, whatever, and then the exponent. Doubles, 8 bytes wide, much larger, can have about 15 digits of precision on this side, and the exponent can go up to 308. So they're much more accurate, but it's still not precise. You still get floating point errors. And so let's see if I can generate an example of a floating point error, and I hope this is not the one that I did in the past. So here's what I'm going to do. Instead of 1/3, I was having trouble getting 1/3 to work when I was trying to demonstrate it last. So I'm going to say x is equal to 0.8. Well, how about double x is equal to 0.8. Double y is equal to 0.6. Now if I add 0.1 to 0.6, I should get 0.7. And if I subtract 0.1 from x, it should also be 0.7, right? Let's try that. X minus equals 0.1, right? Should now, where did my typing go? Okay, for that, x is equal to x minus 0.1, right? Y equals y plus 0.1. Those should equal the same thing, right? You're yelling at me, just tell me that the assigned values are never used. Well, okay, fine. Why don't we print them out? System.out.println, you know, x plus a comma, in quote, plus y. Let's make sure they're about 0.6. Are they? Excuse me, 0.7. Well, lo and behold, 8 minus 0.1 is not equal to 0.7. Not the same as 0.6 plus 0.1. They should be, right? So if you did this, if x equals y, print yes, else, you know, print no. It's going to print no. They're not the same, even though they should be, right? So what do you got to do? You have to create, you know, an acceptable error value. I believe that's called sigma or something like that. So you take the absolute value, the difference, and then you check to see if that value is less than your acceptable error. Like, what if 0.1 is an acceptable error, right? So that 0.6 and 0.5 would be acceptable. That's pretty sloppy, but you know. Or 0.001. If two numbers differ by 0.001, then it's acceptable. And if they differ by more than that, it's okay. So we're going to do that. So I'm going to declare a double called acceptable error. And I'm going to set it equal to 0.0001, right? So if two numbers are within that amount of each other, if you took the difference between two numbers, if that value was close enough, then they would be considered equal. So we're going to find out the actual error. We're not going to call it error, but we're going to call it delta. It's the difference between the two values, right? So double delta is equal to x minus y, but we need the absolute value to make it easier to check, right? So math.abs parentheses x minus y in parentheses, right? That's how far apart they are. System.out.println, you know, delta equals, in quote, plus the delta. Let's find out how different they are from each other. That's the difference between them. That's a very small number, right? It's a 0 followed by 15 zeros, or excuse me, a 0 followed by a decimal. It looks like this, right? 15 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and then all these digits, right? Whatever, right? It's a pretty small number. That's the difference between the two. That's how close they are. So we could do, if the delta is less than the acceptable error, acceptable difference, might be a better term, right? I'm not going to change it now. Then print yes or no, right? Cout, or what, cout? That's C++. System.out.println, close enough. Else, I'm going to remove that brace. Else, print not close enough. And they are going to be close enough, right? Because that value of the delta is certainly less than what we defined as the acceptable delta. That would have been a better word, right? Acceptable delta, acceptable difference, right? Acceptable delta. There we go. They are close enough, right? Because they only differ by 0.00000001, right? Two numbers that were further apart, not match, right? So if I went up here and said, well, x is equal to 0.2, and then I said y is equal to 0.3, right? And then I ran them, well, those are not close enough. So we're going to see the message not close enough, right? Because the difference between 0.2 and 0.3, that's the delta. Again, you'd expect it to say 0.1, but instead we have a rounding error again. So even doubles with their 15 to 16 places of precision are not accurate, right? Or I should say, they still get rounding errors. You can't say that they're not accurate. It's just that they have a limit. There's a data type that works a lot better because it has more digits of accuracy allocated to it. It's called big decimal. There's also a replacement for long and for integer called big integer. Let's create some big integers. I'm going to come up to the top and add an whoa, it's already there. Just add java.math.asterisk so that we get the big integer and the big decimal classes. All right, you need to add that. All right, so I'm going to come down here and I'm going to create a big integer. Big integer b1 equals new big integer parentheses quote, and I'm going to turn the value 100 into a big integer. Now it's still equal to 100, right? It's just a different data type. Just like you could store 100 in a float or a long, or a double, or an integer, still a value 100. Just a data type capable of holding larger numbers. Now, did we need to store 100 in a big integer? It's like putting a small, package on a, what do they call it? Whatever, a semi truck, right? Giant dump truck. You don't need that big of a vehicle in order to carry that small of a value. But we did, okay. And then we're going to do another big integer, but I want to make it out of a long. Now I wish I could do this, but for some reason, so don't even type what this is going on. I wish that I could say, I want this number right there, that long value, to be turned into a big integer. But for some reason, they made the constructor accept strings rather than longs. That doesn't mean that you can't create a big integer from a long. You just have to use a different creation syntax, right? Big integer, parentheses, dot, value of, and then you can stick your long in there. Now, as we've said before, the maximum value for an integer is about 2 billion. So let's put a number in there that we know is larger than 2 billion, like 99 billion, 99, and then followed by 9 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9. Whoops, whatever, right? Okay, there we go. So that's a fairly long number, right? It's too big to fit into an int. Not too big to fit into a long, but if we started multiplying it or adding it to itself or something, then we would get to the point where it would no longer fit into a long. Let's see if we can get to that point just by making a loop that keeps doubling, right? So we're going to say that int, and what am I going to call this value? A is equal to, 1, and we're going to start doubling it. We're just going to keep doubling it until, we're out of luck. So for parentheses, int I equals 0. How about 1? We're going to double it one time. I is less than or equal to 10, semicolon, I plus plus. What are we going to do? We're going to say A equals A times 2. You could just say A times equals 2. What is I already declared? Oh, I don't have a semicolon there. All right, and we're going to print it out. System.out.printf. Not printf, let's do it easy. Print ln, A equals end quote plus A. Why don't we prefix this with a word integer? Integer A equals, right? And we'll just watch that thing double until, well, it's going to be doubled 10 times. Let's find out what happens if you double a number by 10 times. Alrighty, that wasn't enough to prove anything. It only got, 2 to the power of 10 is only 1024. Why don't we make it double it 20 times? All right, still not big enough to be impressive, right? Let's do it 30 times. 40, right? Why be conservative? If you take the value due and you double it 40 times, at a certain point, it goes kablooey, right? So I don't know what I was equal to at that point. We should probably print it out because that is a point of interest, right? The point where it proceeds from being an accurate value to an inaccurate one. So why don't we print I as well? So let's do system.out.println doubled end quote plus I, right? So we're just going to keep track of how many times we've doubled that number based on our I counter. How many times? Let's find out. We were able to double it 31 times, or at least you could say 30 times. Doubling at 30 worked. Doubling at 31 caused it to corrupt the data. We exceeded the maximum size of an int. Well, look at that. It's probably when it got larger than 2 billion, right? Because 107 whatever, 1.07 billion, if you double it, is larger than 2 billion, so that's where it got corrupted. What are we going to do now? We're going to take the same code, but we're going to use a long. We're going to see how much long, okay, well, we know that it got up to about 30, right? 31 times? I don't remember. 31 times is when it croaked. So I'm going to make our for loop double it a maximum of 31 times. Just so we don't see a whole bunch of, corrupted data. 1 is enough. Right? So after the 31st doubling, the data was corrupted. And that's for an int. So take all this stuff, copy it, and we're going to use a long instead. So we're going to wind up changing all these A's to like B's or something. So long B equals 1. And then change all these other A's to B's, right? Make sure you get them all. So what did I change? I changed that line, changed A from B, changed the data type to long. I changed that line, B equals B times 2, and I changed this line. You used to say integer B is equal to, okay, let's make it say long B equals, there we go. Now it's not going to get corrupted after 31. We're going to have to, crank up the limit to a larger value to see it get corrupted. All right, so the 31st doubling didn't phase it at all. Let's do it to 50. Nope. We were able to double it 50 times without flaw. 60. Is it going to work at 60 and fail like it's 61 or something because it worked up to 30 and failed at 31? Let's find out. So 60. Still kept working. Let's try 70. Run it. Alrighty, somewhere between 60 and 70, well, 63. Once it doubled that number 63 times, it exceeded the capacity of a long to hold it. And we could repeat the same process with a float and a double. We could find out where it corrupts. Let's just focus on the integer data types. So after 63 doublings, it's corrupted. We could make a little note, right? Int corrupts after 31 doublings. Long corrupts after 63 doublings. All right, how about a big integer? When will it fail? When we start doubling it. How many times can we double it? Let's find out. Let's make a new big integer, right? Big integer, you know, big 1 equals new, or how about big integer dot value of 1, right? Let's do the same thing. We're going to copy this loop here from there to there, and we're going to change all the b's to big 1. That's probably not going to print out correctly. I don't remember if the toString method works or not on this thing. Oh, surely it will. All right, so big 1, change all these b's to big 1. There's 2 of them there. There's 2 of them here. So big integer big 1 equals, all right, there we go. Except that's not how you multiply, right? We're going to have to change that line completely. It's going to look like this. Big 1 dot multiply by 2, right? That's how you do it. That's how you double, well, it's how you multiply. We didn't need 2 parentheses there. That was kind of dumb. Ooh, why are we getting a syntax error there? Multiply long is not in big integer. Oh yeah? So our problem is that the math methods dot multiply, dot divide, dot add, dot subtract, dot modulus will not work with the primitive data type there. If you're going to do math on a big integer, you can only do math with other big integers, right? If you want to add a big integer, you can't add a big integer to, you know, an int or a long or a double or whatever. You're going to have to add it to another big integer. So we need to make another big integer equal to the value of 2, and then we can multiply them together. So let's do that. Big integer, big 2, equal to the value of 2. What a coincidence. Big 1 equal to 1, big 2 equals 2. I like the symmetry that's going on here. Let's show the other syntax. Equals new big integer, parentheses, quote 2, end quote, end parentheses, semicolon. Just to remind ourselves that we can create a big integer from a string, which is what the book loves to do. It's not the only way it does it. And then by using not the constructor, not using a new keyword, but by calling big integer dot value of. All right, and so down here, when we're multiplying the values, we're going to multiply big 1 by big 2, right? See that? Big 1 dot multiply, parentheses, big 2. And since big 2 is equal to the number 2, that's going to double it each time. Now, let's see if doubling a big int 63 times causes corruption. Let's find out. Oh, what do you know? So the answer is that big 1 dot multiply big 2 does not change the value of big 1, but it does return a new value based on big 1 and b2. I guess, like, right, 2 times 3 does not, whoops, that should have been a 2. 2 plus 3 does not change the value of 2. 2 stays the same, but this does return a new value. So here's what we're going to do. We're going to say big 1 equals big 1 dot multiply big 2. So we have doubled the value. It returned a result that was 2 times the original value, and we store it back in a big 1. Let's run it. Okay, it doubled it 63 times. Worked. Let's get ambitious. Double it 100 times. Ooh-wee, that's a really big number, far longer than a long can hold. I'm not sure that's true, but let's keep going. Yeah, it has to be, right? Because we've doubled it 100 times, and we could only double a long like 62 times before it messed it up. How about 200? Alrighty, how about 1,000 doublings? Nidokeen. We have doubled that number 1,000 times, and it's still not corrupted. Does it ever corrupt? Do it 100,000 times. I mean, it can't be infinite, can it? All right, this is taking a long time to run. I'm going to minimize it and then bring it back, see if it speeds it up. Because it's printing to the screen, that's taking by far the most time. If we didn't have a print method in there at all, then it would run in a fraction of a second. Let's take a look. Okay, I think that's enough to prove the point, right? This is a huge number. If I scroll over here, right, that's a large integer. You need a big number? Go for it, use a big integer. Big double works about the same, right? You create a big double. If you want to multiply a big double by another big double, let's play with that. Just make sure we got the concept. That's about we stop it. I'm going to come down here and click the little click to cancel process. All right, we never managed to break it. I'm just going to change that back to 100. Right. Let's make a big decimal. Big decimal equals new. Or how about just big decimal equals big decimal parentheses quote. No. 0.0000001, right? Semicolon. Should have been dot value of. And I forgot to give it a variable name. Cute. So it's actually a big float, right? But they're calling it big decimal. All right, so I'm going to call it big float 1, BF1, right? And then we're going to, I don't know, divide that number by a huge number, right? So big decimal BF2 equals big decimal dot value of. You know, 1e to the 100, right? 1 followed by 100 zeros. Ooh, it didn't like that. Semicolon expected. Why? Where am I missing my semicolon? My eyes are getting old. I made a minus. Should have been an equal. Okay, so big decimal BF2 is equal to big decimal dot value of 1e to the 100, right? A 1 followed by 100. Now let's divide BF1 by BF2 so that we get a very, very, very small number, right? Because that's already small and we're dividing it by, you know, a super quadrillion, million, billion, whatever. Alrighty, so BF2, or how about, you know, big decimal BF result equals BF1 dot divide by its divisor, which is BF2. And let's print that out. System.out.println parentheses quote BF result equals end quote plus BF result. Small number. What are we going to do? We're going to keep dividing it by 2 until it gets really, really, really small. We're going to keep dividing it by BF2 so it gets small really fast. Do we have a while loop? Anyways, that's how you do it, right? You create some big decimal values, you call dot mult, or multiply, or dot divide, or whatever you need to do your math to it. Dot add, dot subtract. Hope that makes sense. Hope that makes sense. I don't really feel the need for us to talk about big decimal, big integer more than that. I also don't see much of a reason to assign homework over that concept. But just do know that you can use the concept if you need to store data values that are more precise than a double, or larger than a long, or something like that. Then you would use big integer and big decimal. Let's see what else in the PowerPoint's a good thing to know. This is interesting. Big integer for cryptography. The RSA algorithm. Well worth reading if you're taking cryptography courses, which we have here. You may be doing the cybersecurity path. The CareType. What does a care hold? It holds an ASCII value, right? If you could zoom in on this, you'd see the ASCII value of an A. Well, I don't see where it is. Here it is. The ASCII value of a large A is 65. The ASCII value of a C is 2 more than that, so it's a 67. You just got to have some numeric value to equal a character, right? Because you have to have some way of storing this English text or whatever it is into memory. We already knew that, didn't we? I bet we did. So if you're going to print something out, if it's a character, you can append it to a string, right? What happens if you didn't do that? Well, if you try to concatenate 2 characters together, it's not going to work. Let's demonstrate that. We could create 2 characters. Char C1 equals an uppercase A. Except since it's a character, we got to put single quotes around it. Apostrophes. Char C2 is equal to an uppercase B. Now let's add them together. Let's just print them out. System.out.println, C1 plus C2. Is it going to print AB? Be neat if it concatenated them together. It's not gonna. Print something completely different. 131. Why? Because A is a 65, B is a 66, and so it just tried to create a new character with the value of 131. So what are you going to do? You want to print it as a string, you just concatenate it to a string, right? Empty string plus something else is always a really fast way of converting something to a string in this language. And now it's going to print AB. Right? Cool deal. Be aware that if you use a plus operator on 2 characters, it does not perform concatenation. Instead, it does math addition using a character's underlying ASCII values. The Unicode standard. Well, the problem with ASCII is that it only specifies 128 different letters. Uppercase, lowercase English, punctuation, and whatever. Obviously, there's a lot more letters than that on the planet Earth, right? There are Russian letters, there are, German letters with all the diacriticals, umlauts, and stuff like that. Japanese, Chinese, Korean, African languages, this, that, and the other, way, way, way more than 128 different characters. And so the powers that be created something called the Unicode standard. Huge set of 65,000 different characters, which is enough for, English and Russian and German and, every type of different character, right? Pretty much every language on the planet. Maybe not every language on the planet, but an awful lot of them are on there. And who knows, they may have added Elvish and Klingon and Dothraki by now to it. Have no idea. Also, each time your phones are expanded with new emoji, right? Maybe there's a new emoji for it, a smiley face, that's been split in half. I don't know, whatever. Each time new emoji are added, they have to be encoded as Unicode characters as well. So, because they have to be, a series of numbers that can be transmitted over the internet, just like, alphabet characters. Since the ASCII character set was and is such a popular standard, it was invented in the 60s, and since it was invented by, American and English programmers, that's why it's got all the American English characters. Unicode adopted those as part of the Unicode character set. So a 65 in Unicode is a capital A, just like it is in ASCII. But past that, all bets are off, right? We could try to write a program that would print out a whole bunch of characters to see what they look like. Let's see if we can do that. All right, so C1's already a character type, right? It's capital A. How about this? For A equals, no, let's do a counter. For int I equals 1, I is less than or equal 1,000. Right? I plus plus, gotta have the semicolons all in the right places, even if I don't say it. All right, we're gonna add 1 to C1, right? C1 equals C1 plus 1. So it changes from a 65 to a 66. It goes from an A to a B. What's going on here? Possible lossy type from int to character. Okay, fine. We're going to do what's known as casting. Casting is another part of this chapter. I really thought we'd done it in the past. But here we go, right? Turn this number 1 into a character. Are you still going to keep complaining about lossy integer types? All right, I accepted its hint, right? I let NetBeans give me a hint, and it came up with one. So C1 is the casted value. I could probably get rid of this one now. Let's see if it complains about that, right? So if you take that character and you add 1 to it, and then you cast it back to a character, it can be stored in a character data type. And we can print it out, right? System.out.println, right? Char space end quote plus. Well, really, since this is a 65 and the A is a 65, you know what? Let's just do this. We're going to start I at 65. We're going to keep it going to 1,000, and we're going to create a new character each time by saying there, right? So the first time it's going to be a 65. It's going to be an A. The next time it's going to be, the third time, since I is going to be a 67, it'll be a C, and so on. And we could system.out.printf, parentheses quote, Unicode space %D equals. You know what, I'm not sure if that's going to work, so I'm just going to do it the old way, using println. Println, parentheses quote, Unicode space end quote plus I plus beginning quote space equals space end quote plus C1, right? So it'll print A, B, C, D, E, F. It'll say 65 is an A, 66 is a B, and so on. Why don't we just go up to like 100 first, so we can make sure it's working, and then we'll let it go crazy going up to 1,000, something like that. All right, and so right, A, B, C, D, E, F, all the way up to Z, which is a 90. And then there's a few more random punctuation, and then it starts going. Let's take it up to 128, the maximum ASCII value. ASCII is only a 7-bit standard, so people came up with, extended ASCII that had other character sets, other characters down for the next 128, box drawing characters and hearts and things like that. All right. And so it got to 126. All these look good. It didn't really know what to do with 127 and 128. Yeah, let's print them out to 500. Ooh, look at all these different character types. A U with that symbol above it. Excuse me, that's an O, isn't it? But I was looking at that, all right? Funky things like that, or that, right? These are all part of Unicode. Let's keep going. Take it to 1,000. All right, there's a lot that it doesn't even understand, right? And so we were seeing some squares or spaces up here, but there's, you know, ever need a itchy bitchy little y? I don't know what that is. Some line drawing characters for drawing boxes on the screen, right? Whatever that is. Upside down K. Cool deal. I wonder what that is. If you ever seen the rock band Blue Oyster Cult and their symbol, it kind of looks like that, except it's flipped upside down. There we go, right? No, wait. That's not right. Anyways, yeah, if you flip that upside down, who cares? All right, that's Unicode, right? It's just using more than 1 byte to hold a character, which is what ASCII does. 1 byte equals 1 character. And in this particular language, a character in here is a Unicode character rather than an ASCII character. As opposed to if you're using C++, a character is still an ASCII character. And if you want to hold a Unicode character, you have to use a slightly different data type to hold it. So typecasting. Here's a double. X is a double, but you want to turn it into an int. If you did not have that, the compiler would flag that as an error. Possible data loss. What kind of data is going to get? Well, you know, an int can only hold whole numbers, so it's going to do truncation where it loses the .6, right? But if you add the cast into it, you know, like casting metal, you're remolding it into something else. Then the compiler says, okay, yeah, you know what you're doing. You're accepting that there's going to be some data loss. That was your goal. I mean, it wasn't your goal to lose data, but it was your goal to turn this double into an int doing whatever is necessary, which is losing the decimal point. The conditional operator. The conditional operator is just a very, very short if statement in effect. What if I wanted to do this? What if I wanted to say, you know, int w, you know, and then int w2 is equal to 100, and then we wanted to write something like this. If w is greater than 50, then we want w equal, or we want, yeah, if w, oh, why did I not choose better letters in this, right? Okay, fine. Let's just check to see if these two guys are equal, right? If C1 is equal to C2, right? So string EQ if C1 equals C2, then EQ equals, quote, yes, semicolon, else EQ equals no, right? And then we could print that out or whatever we needed to do based on that, right? So if those two values are equal, which they're not, then this string would get set to yes, else it would get set to no. That's 4 lines of code. Yeah, conceivably you could shorten it to 2 lines of code if you like, you know, writing non-standard formatting like that, right? So I'm going to undo that change. But you could write it like this. EQ is equal to, and I'm going to put parentheses here that are not strictly necessary because I think they make the syntax cleaner. C1 equals C2, just like we had here. And then we put a question mark. So is C1 equal to C2? If so, set EQ equal to the word yes. Then you put a colon, else sets EQ equal to the word no. Those two things do the same thing. Question mark is a conditional operator. Some people call it the ternary operator, ternary meaning 3, just like binary means 2 and unary means 1, because it's got 3 parts, right? It's got the value before the question mark, it's got the value after the question mark, and then there's a third value after a colon. This is not necessary, but I think it makes it code easy to read. Your mileage may vary. All right, next thing that we're talking about is, well, why don't we keep going through the PowerPoint. See here, is x greater than y? We want to return x, else we want to return y, right? That's what this means. It's like an if statement. If x is greater than y, then set something equal to x, else set something equal to y. So say we have a number and we're going to set it equal to positive or negative, right? X is equal to 10. If our number is greater than 0, we want to set a variable equal to positive 1, else we want to set it equal to a negative 1. What if it's exactly equal to 0? What are we going to set it to? I don't know. That's more than 2 choices. We'd need a third choice. Let's just run with it. So, string is pos if x is greater than 0, question mark, set is pos equal to capital Y, otherwise it's not positive. There we go. And if we print I pos out at this point, I seem to have a syntax error here, done something wrong. It's because you don't use the word if there. See, is pos is equal to that stuff, right? It's going to equal either yes or no based on whether that is true or false. So that's the conditional operator, the ternary operator. Why do you do that? I guess just to save space, or if you wanted to put this inside of a method. What do I mean by that? As an argument to a method. If you're going to put it as an argument to a method, right, what if we wanted to set this variable equal to one thing or another thing and then pass that to a method? Right, we might have a sample method like math.isPow, right? So double, DDD is equal to math.pow, DD2 to the power of 10. And DD2 is either supposed to equal 2 or negative 2 based on some condition, right? So we would have to have an if here, right? If something, something, blah, 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 then DD2 equals something else, DD2 would equal something else. Instead, we could write that expression right here, right? And so, if x greater than 0, question mark, else the argument had better be a 1, colon, else otherwise the argument is going to be a negative 1. Now that's kind of dumb because 1 to the power of 10 is still 1. So let's make it say, 2 or negative 2 based on the value of x, right? So is x greater than 0? Yeah, then pass 2 into our function. Else pass negative 2. Now to my mind, that's a bit too clever by half, and that's the kind of thing that you see C programmers doing because C programmers, I don't know, they like to save space in their code, put a lot of things on one line. That's a generic thought. I'm not sure if you consider that accurate, but that's my experience, is that people who grew up learning C is their first language of choice. There's a lot of code examples on the internet, and you'll see that they write code in as terse a format as possible. That's pretty terse, all right, but honestly, I would probably rather have some kind of if statement that would set a variable equal to something, and then I would just pass that variable into that function. Make it a lot easier to read. So grade equals, is their score above grade greater than or equal to 60? Then grade equals pass. Else grade equals fail. Short-circuit evaluation. I swear we've talked about that before, or we should have in an earlier chapter. Short-circuit evaluation just means that if you're using AND, if this can be disproven and it's false, there's no reason for the code to go ahead and implement the other part of it, right? Because if this is false, what does AND mean? AND means both sides have to be true. So if the first side is false, it doesn't bother to even implement the second side. On the other hand, if that was or means either one side or the other has to be true. So if this part is true, it doesn't have to do the rest of it because it already knows that the expression is true, because that's enough to fulfill the condition of an or. So that's short-circuiting evaluation, and the reason why the code does that is just to speed things up a bit, right? Because this second half may be some function, some method that has to be called that takes, 5 seconds to run, or, a whole bunch of time. If we can skip doing that because this side had to be false or whatever, then great, right? You save a whole bunch of time. Usually you're not going to save a whole bunch of time, but that's still a finite amount of time that has to be executed in order to do the second part. And if the compiler can set it up so that the second part is skipped based on the value of the first part, so much the better. So short-circuiting isn't bad, it's a good thing. So short-circuiting of AND. Say you have the expression X and Y. If X is false, the code doesn't bother to evaluate Y, because AND requires both sides of the ampersand operator to be true. And so if the first operand is false, it doesn't do the second. And by operand, we mean whatever expression is there, right? If I is equal to 0 and B is equal to 1, right? If I is not equal 0, it's not going to bother doing that. Short-circuiting of OR. Say you have the expression A or B. If A is true, the code doesn't bother to evaluate B, because OR requires only one side to be true. Only one side of the OR to be true. And if it is true, it can skip the second part. So short-circuiting isn't bad, it's good. Speeds things up. It's not like, oh my gosh, the engines are short-circuiting, Captain. We better shut down the warp coil. Right, whatever. It's a good thing. Speeds the code up. The only thing you need to be aware of is the fact that it does occur. So if your code looked like this, if A is equal to 0 and B, well, let's call test func, passing in A is equal to 7. If for some reason your code depended upon that being called every single if statement, for some reason you wrote it so tightly coupled that had to be called with every if statement, it's not going to work right, because it'd only be called when this happened to be true over here. would skip being called. So if you have methods that absolutely must be called before the if statement executes, you better either put it on this side instead, or you better call it before the if statement to prove the point, right? But you could put result equals test func A, and then you could just say if A is equal to 0, or result equals 7, or and result equals, right? That way you're guaranteed that this function, this method is going to be invoked every single time. Short circuiting is not unique to C++. It's also in C and in Java and C#, and I believe it's in Python, right? Just because it speeds things up. What if test func took, 0.5 seconds in order to execute? If you could skip that by using short circuiting, then the code would run much more quickly. A side effect is that you want to rule out as many things as possible, right? Because if you can rule out as many things as possible, it has to evaluate that one less often. So you want to put the thing that is false more often first, right? Because that means that the second part can be skipped more often. The more often the first part is false, the more times that the second evaluation is skipped. Or is opposite, right? Because if this is true, it skips the rest of it. So if you're using or, the first expression, you want to put the expression that is true most often first, so it can skip the second evaluation. So for or, well, let's do it for and, comma, put the expression that is false most often as the first operand, or the operand before the ampersands, right? For or, put the expression that is true most often as the first operand. And you just do that so it can skip evaluating the second operand as many times as is possible. The empty statement. The empty statement is something that does nothing. It's a semicolon all by itself. Use the empty statement in places where the compiler requires a statement, but there's no need to do anything. For example, this for loop can be used as a quick and dirty way to add a delay to a program. Start I at 1 and count up to I is equal to billion. That's kind of a silly way of putting a pause, but it certainly would work, right? Or you want to, double the value of I 10 times in a row, right? Or you want to keep doubling it until I is, greater than 1,000 or something like that. You don't necessarily need a body to accommodate that. So you just use a semicolon there. It's the same thing as if you put there, right? So if you did this, go pick a variable we already have, right? Some int or something like that. B, long B. And you just feel like doubling B 10 times, you don't necessarily need a body to do that, right? So for int I is equal to 1, keep running as long as I is less than or equal to 10. What are you going to do? You're going to add 1 to I, comma, and you're going to double, I've already forgotten what I said that variable was called, D, right? D times equals 2. Don't do anything, right? Ooh, why are we getting an error there? Cannot find symbol D. Really? And what did I have up here? All right, B. We had the variable B. Excuse me. Right. There we go. This would double B every single time. Okay. Now that's kind of silly because you could put this into the body, right? But there may be some evaluation here that doesn't require a body at all. So you could put that there, right? Keep running. Keep running until, we have exceeded our condition. But there wasn't really anything we needed to do in there. We weren't printing. This is another kind of thing that you see C programmers do. They like writing while loops that have everything in there and then a semicolon at the end, because an empty block is the same thing as doing that. Just do that, right? Repeat it that many times. Another example, right? Int I1 equals, 2, comma, I2. And let's just leave that alone. While, well, let's do it as another for loop. My brain works in terms of for loops better. So for int I. Now I'm going to set it up as a while loop. Int I2 is equal to 1. And so while I1 plus plus, or plus plus I1, plus I2 plus plus, this is getting really nasty looking, right, is less than 1,000, keep going. So what is that going to do, right? It's going to keep adding 1 every pass through the while. It's going to keep adding 1 to I2 through the pass. But there's nothing else we need to do. We just wanted to increase those values as long as 1 multiplied by 2 was less than 1,000. After we're done, we could print those out, right? System.out.println I1 plus a space plus I2. Who knows what those values are going to be? I can't predict them in my head. All right. So it looks like it ran about 32 times before that value times that value was no longer less than 1,000. And again, we didn't need to do anything in the body, so we just put a semicolon there. Well, there. Now, in your early programming days, you were prone to putting semicolons after for statements and while statements and stuff, and the reason it broke is it meant do this empty stuff as long as this condition is true. And that can result in an infinite loop real easily, right? While I2 is less than 1,000, semicolon, system.out.println I2, right? This is an error. Why? Because it's the same thing as doing this. Don't do anything while I2 is less than 10,000. Keep running though. Just keep doing it, and it's going to do it forever. That's an infinite loop. How would you fix that? You needed an I++ there, or I2++. You needed some kind of update there. And if you had a semicolon there, ruins it. It repeats this comparison forever without ever executing anything else because it's executing an empty statement. All right, I think that's about enough. So we need to look at projects. The way the projects are going to work is, since this is week 12, you got several weeks, 13, 14, 15, right, 16. You can skip taking the exam, the final exam, if you do a good job on the project. So you're going to want to get the project done as fast as possible so that I can tell you, yeah, that was a good project, so you can skip the exam. Or if you don't want to do the final project, then you just do the exam. You can make that decision. So some project ideas, things that you could think about doing. Can I zoom this in? Can I get a scroll bar for zooming in, please? Yeah, it's looking pretty bad. All right, fine. First project idea, linked list. You could research how to make a linked list in Java, writing your own class, not using one already built into Java. This is the one project where it is okay to use code from the internet. I'll send you the website that I want you to use that has sample code. So your project should use the linked list after you create the classes based on the code that you either copy from the internet or you write yourself, and in the interest of time you may just want to copy it. And you're going to add, remove, and display items in the list as specified in the requirements. So the project, okay, you already know how to create classes. Since you might be using code from the internet, you also need to write a short 2 or 3 paragraph explaining in your own words what a linked list is, right? Without this, you do not get full credit for the project. So baseball, another project idea. This game will use random numbers to decide whether the batter strikes out, get a home run, etc. So you have a lot of freedom in this one. You can pick the rules that you want to implement. I was imagining something like this. Welcome to the baseball simulator. How many innings do you want to play? So team 1 takes bat, right? So team 1, batter 1. He strikes once, he strikes twice, he strikes 3 times, he's out. You get to decide what caused him to strike, right? Is there a 30% chance of a strike? Is there an 80% chance of a strike? You generate a random number and you compare it to something, and that determines whether he strikes. So we have some kind of counter. It warns us that was 1 out of 3 strikeouts. So second batter comes up to bat. Team 1, strike, strike, home run, right? So whatever random check you were doing, happened to return a true, so that a home run was generated and the score is now 1-0. Third batter comes up to bat. He strikes out. So he's out. That was 2 out of 3 strikeouts, right? And then team 1, batter 4. He got a home run right out the bat, so now the score is 2-0. And so on. You would play until team 1 had 3 strikes, right? 3 strikeouts ends the inning for that team. I believe that's the rules for baseball. If it's not, correct me and do it the correct way. Then team 2 would take the bat and repeat the process, right? Maybe you make it so that team 2 strikes out more often, whatever, or that they score home runs more often. Now, this is only showing a choice between getting a strike and getting a home run, but obviously in baseball, you can get singles or doubles, and that means that the person can run 1 base or 2 base. If you feel like it, you can make it a lot more complex than what's shown above. Not just using strikeouts and home runs, but singles and doubles and which player is on which base and so on. Feel like making it more complicated, that's totally cool. Football. Write a football simulator that uses random numbers to determine how many yards that the player gets each time. Failure to get 10 yards and 4 downs causes the other team to get the ball. And if you're a football fan, you know all this stuff probably better than I do. So you can assume the game ends after 60 plays, right? 60 random numbers generated or whatever. It's not too far from the truth in a pro football game. Sounds weird, right? But in actuality, in a pro football game, the players are actually moving and running and stuff like that for only 12 minutes out of a 90-minute game. That's because the rest of the time is, setting up the play and, walking back from the results of the play and stuff like that. Turns out to be about 60 plays, So, or you could say that each play takes a random amount of time. So you have complete freedom to make the code. You want to make it simple or complex? Does it support passes as well as runs? Will it support field goals, touchdowns, extra point kicks? Make it awesome if you want. I mean, I would love for it to be awesome. Even implementing something simple is awesome, but it can be even awesomer, if that was a word. So do passes earn more yards but fail more often? Right? How does it pick whether it's going to do a pass or fail? So one team would get to play until it failed to make, the 4th down. Then the other team would get to make a play. And you just need to be keeping track of the number of plays. You know the rules for football. Presumably, if you don't, I wouldn't choose this one. Same for baseball. Then something called C# Fighter, although I'm going to rename that to Java Fighter. Sorry. So are you a D&D or Pathfinder fan or whatever? So I'll give you simple rules for a game where 2 fighters have an attack strength and an armor rating, and then they fight it out until one player is reduced to 0 hit points or below. Or you can make the idea better than what I give you. One player did a Pokemon game where the player selects a Pokemon, the computer does too, Random attacks are picked. You know, some attacks work better on certain Pokemon than others. So it was a pretty cool project. So Caesar's Cipher. Maybe you remember Caesar's Cipher from another game. TEF project? That should be the project. I will specify 2 algorithms of Caesar's Cipher, a simple one and a complex one. So you can read about Caesar's Cipher if you don't know what it is. Also my explanation. It is well documented in the instructions I will post. So you will let the user pick which algorithm to use and whether to encipher or decipher. Right? So it'll say, you know, use simple or complex. They pick one or they pick the other. And then do you want to encipher or decipher? Because one is doing the opposite of the other. And then you let them type in some text and it does the cipher. Then they could run it again, deciphering the same text, and hopefully they get this original. So, although this says, there's something missing here. Where did Hangman go? Okay, Hangman. Implement a game of Hangman. The computer picks a random word and the player guesses letters until they either fill the word in or run out of guesses. Would say that 10 bad guesses ends the game, or if you think fewer is fair, go with that. Warning, quite often in the past when for Hangman, and this is serious business, if you go on the if you go on the internet and download a Hangman program and submit it, you're going to fail the project and it's going to be called academic dishonesty and there are going to be serious consequences. So what often happens is that people think, ooh, the Hangman project, that sounds simple, I know how to play Hangman. And then they wait several weeks and then they go into a panic and they download something from the internet and submit it, and then bad things happen. So I can tell usually find the exact site that the copied code came from. So don't do it. Don't wait until the last minute. And if you get stuck, I will be happy to provide you with a flowchart that helps you do this. It's not a really difficult project if you have that flowchart, but try it yourself first. And I repeat, don't download code from the internet. That's true of all of these, right? But you know, it's happened a lot on Hangman projects in prior semesters, so I'm trying to, you know, ward that off by giving you a warning. Don't do it. Caesar's Cipher code is also out on the internet. You can just copy that, paste it, upload it, and say, yo, I turned in a Caesar Cipher project. No, I give you specific algorithms to use. You know, they're not complex algorithms, but I give you specific ones. The reason I do that is that I know you did the work. A little bit different than the Caesar Cipher code you will find on the internet. You'll have to research it if you don't already know what Caesar Cipher is. I know that if you've taken, you know, cybersecurity course or whatever, it's a really easy concept. If you want to do that one, you know. So, or your own project. If you have an idea for your own project, you can mail it to me.
Oh, thank you.
Send a text saying that you did so, right, so that I'll answer your mail as soon as possible. Make it interesting, make it not too easy, not too hard, right, because we have limited time, you know, until week 16 to get this done. So if it turns out too hard, despite your initial prediction, you could always change your mind, like do Hangman from the flowchart, or you could just say, nah, forget projects, I want to take the final exam. Right? I'd rather you do a project than an exam, but it's up to you, right? Time management. All right, hope that makes sense. Do a project if you want. Successful completion of a project lets you skip the final exam. Don't want to do a project, take the final exam. I give you some ideas. You feel like doing your own ideas, that's great. Just mail it to me, let me know. All right? Make sense? Like I said, I'm not going to give you homework over this chapter because other than big integer and big decimal, maybe I ought to give you some homework on that. I don't know. Yeah, why not? Why not? Let's use big integer. Homework. Demonstrate that you know how to use the big integer class. Ask the user for 2 numbers. Ask the user whether they wish to add, multiply, subtract, or divide the 2 numbers. Use big integer to do the math and then print the results. Right? So something like this. What is the first number? and say they type in, 999 billion. So 999, 1, 2, 3, 4, 5, 6, 7, 8, 9. There. What is the second number? And they type in 1 billion. 1, 2, 3, 4, 5, 6, 7, 8, 9. What do you wish to do? 1 equals, 1 equals multiply. 2 equals, divide. 3 equals subtract or add. 4 equals subtract. They choose 1. Right, they want to multiply those numbers. And we can print a little message. The result is, what is it? Well, just like that, right? There we go. All right, now this would be pretty hard to do if these numbers were too large to fit into longs. They're not, but you could conceivably add so many zeros to it, 108 zeros, you could. That would be too big to fit into a long, right? So, I hope that makes sense, right? Pretty short little program. Hopefully you can look at the book for examples of how to use big integer. You can Google up for examples of how to use big integer, right? All you're going to have to do is convert from this string that they type in into a big int, and we demonstrated that several times. And then how you call, big int 1 dot multiply parentheses big int 2, something like that. Just remember that both things that you're doing, the number and then the number you're multiplying by, have to be big ints, and you need to store the result in a big int, and then you can print it out. All right, let's call this done.